Alright, so this is a new section, 11. And in this lecture, we are going to talk about some of the new applications of the memory technology beyond the traditional memory application. So here we are going to talk about how we can use the memory into even logic applications. So this is beyond the traditional memory application. So we talk about the emerging long-term memory technologies like the R1, phase change, or the STT-MRAM. And this is the memory hierarchy we have talked about before. And if you look at the possible positions of those emerging technologies, I hope that through our discussions in the previous lectures, you will position those technologies to the suitable locations in this hierarchy. For example, STT-MRAM probably is good for the mass level cache, and then the R1 phase change because of the limited endurance. So probably the storage class memory between DRAM and the NAND flash, and then all of those emerging technologies can be used as the on-chip embedded non-volatile memory. So this is what we are going to discuss. And we see the trade-off between the speed, bandwidth, endurance versus the density or the cost. So this is what we have discussed before. So the good thing about those emerging technologies is that they can be integrated as the backend of the NAND, which means the interconnect levels of your logic chip. So if you don't have a large memory array, you can insert those memory cells even into your logic in the backend of the NAND, in some of the metal layers. So this is how we are going to use that for the logic. We are going to discuss that in today's lecture. So here are questions. What are the new applications beyond memory? So the trend is to bring the memory closer to the logic, right? So this is the general trend because data transfer is expensive in terms of the latency and energy. So here are the possible applications we are going to discuss. So the first one is the non-volatile logic. So this is for instant on, instant off, no power applications. So the idea here is to store your logic state to the non-volatile memory on chip. So then you can power off your chip and then save for the energy during the standby mode. And then you can later turn on your chip. Then you can resume your logic operation right away. So this is one of the application, and we call this non-volatile logic. And the second one is the reconfigurable logic, or for the FPGA, right? So you need to reconfigure your logic, and then you can use the memory to reconfigure your logic function. And the last one is try to merge the memory and the logic, or do this processing in memory. And this is very useful for the neural network or machine learning acceleration. And we are going to have a separate lecture on this, maybe next class. So let's look at the first two in today's lecture. So the non-volatile logic is a promising solution for the low power applications, especially for your edge device. Because in many cases, you are in the standby or the sleep mode for those edge devices. But if you use the conventional logic, you may have the SRAM to store your data, but you cannot really power off the SRAM because it's a volatile memory. But still, what you want to do here is to do the DVFS to save the power, right? So if you are familiar with DVFS, it's like dynamic voltage frequency scaling. So basically, this is standard thing in today's chip, like your smartphone. So if you are in the standby mode, then the VDD is going to be lowered to probably 0.6 volts. When you're in the active operation, maybe 0.9 volt or 1 volt. So, and also frequency, clock frequency can be varied. When you are using the apps, then probably it's running at the maximum speed or even burst mode. So, but if you are doing nothing, then the clock frequency is only hundreds of megahertz. So this is just to try to save the power. But you cannot really power down the chip, right? Because here you can have the this is like your standby period. You cannot power down your VDD because all those will be volatile, and SRAM will suffer the leakage power. Right? SRAM is always leaking. So this is a problem. And if you need to totally power off, like you really push your power button, then probably some of your app data need to be stored in your flash, your non-volatile memory. So then you need some time to do this data transfer. So basically, some of the key data from your SRAM cache, or even some of the logic states need to be saved to the flash before you power off. And later when you power on, then of course you need to load the data in from the flash to your buffer, to SRAM. So, take some time, and you can even feel that when you use your phone, right? So this is slow and consume a lot of energy to just save the data and reload the data. So the idea here is to build the non-volatility into the logic and try to integrate those non-volatile memory, especially those emerging technologies as we discussed, like RRAM or STT-MRAM, into the logic. And then your intermediate data in the logic, or let's say your data in the SRAM cache can be locally stored into the non-volatile memory close by, which you can save the leakage power because you can totally power down the chip. And you can do this very frequently, and because we can power down, power off and on, so-called instantly. So that means you take very short time to do this, hopefully. So this is the key idea. And how do you do this? Okay. So you can look at the key components in the logic. For example, in the logic, you will have the buffer, or let's say SRAM cache, or flip-flop register. So those are the memory to store your data in the logic. And we're trying to have a non-volatile version of that, so-called NV SRAM or NV flip-flop. And also in the logic, sometimes you have this so-called TCAN cell. We're going to discuss that later. This is content addressable memory, and you can have a non-volatile version of that as well. So then the idea is that you can locally store those data into the non-volatile portion of the NVS SRAM cell. Then you can do this dynamic power gating without transferring data to your flash. So this is the key idea. And then let's look at some of the example. Okay, let's start from the non-volatile SRAM first. So think about your SRAM. And here the idea is to add two resistor, for example, to RN cell to the SRAM. And then add two additional transistor, like 221R. So used to be 60 SRAM cell. And then you add two 1T1R. So in total you have what? 8T to R cell. And it's something like this. So here you see the traditional 6T is here. And then the Q and the Q bar, those two storage nodes, you have a resistor, or let's say the R1 stack, to the back end of the LAN through some higher level metal. For example, in this image, you can see it's some higher metal level here. And your transistor for the SRAM is done in the substrate, on the substrate. So here you have two resistors like this, and then of course you have some contact wire and connect to another transistor, and you have additional wire line to control those two. So then how does this work? So
sorry, Professor, the process is a 0.18 micrometer
yes.
ITR hafnium monoxide?
Yes.
Oh, okay.
This chip, yeah, is 180 nanometer CMOS and hafnium oxide R1.
Isn't it 2 after the 0?
Yeah, this is a typo, I think. Yeah.
Okay.
So the way you use this one is that in the normal operation mode, okay, you just want to have the SRAM function and the same as before, so you don't apply any voltage to your SWL. So it's like those two resistors are floating. Then here the connection is not there because they are floating. So then this is just the regular 6T SRAM cell operation. You have the read and write operation to the SRAM cell. Maybe the speed will be affected a little bit because additional like the capacitance due to that contact wire, but overall it's the same function as before. So you do the regular read and write to your SRAM cell. So before you power off the chip, this is what you need to do, so-called the store operation. You need to store the data from the SRAM to the R1 locally. So how do you do that? Okay. So then here, for example, let's say Q stores 1 or stores 0. Let me see. Q stores 1, let's assume Q stores 1, and Q bar stores 0. So before you power off, you need to save this data to the R1, this RL left or RR right. So you need to save the 1, 0 to those two. Okay. So how do you do this? You can first enable the SWL here. This is timing diagram. So first this is store operation. You need to turn on the SWL. So and then apply 1 to both bit and bit and bar. So if you turn on the SWL, basically this transistor is turned on. This is 1T1R, this T is turned on. So you look at this. This is 1 and 1. So this RL sees no voltage difference between those two terminals. So it will not change. But the RR, you see this. This transistor is on, so this 1 is passed to here. So essentially you have 1 here and 0 here. So you have current flow this way. And if this is a set direction, then this RR will be set to the low resistance state. So this RR will change here. If initially it's a high resistance state, it will set to the low resistance state. The resistance will change. Essentially, you are writing the data into the RR, depending on the data pattern you store here. Of course, if your data pattern stored is Q is 0 or Q bar is 1, then the RL will be written. So depending on your SRAM data pattern, then either RR or RL will be written. So this is your store RR, but this is a complementary operation, so you need to do it one more cycle to reset the RL if it's no resistance state to start with. Then now the second cycle is you are going to have bit line bar to be 0. Now this one will have low current because 0 and 0. But the RL, you see here, 1 and 0, so current will flow this way. You see this bidirectional current. So this RR is going to, we discussed, will have this transition. Then this RL will have low resistance state to the high resistance state transition. Right. So then you finish the write operation to the RL. Now, after you do those two steps, now you can power off the VDD for the SRAM cell. Then you don't consume any energy in the standby mode. And your data is locally stored in those two R1 cells. Right. Okay, so this is power off. And after some time, you need to wake up this cell. So then the first thing is this restore phase. So the restore phase, you don't need to do anything. You just need to power up this VDD, because this is a VDD for the SRAM, 60 SRAM. Once you power up the VDD, so the SRAM cell, will automatically flip to this 1 and 0 state because of the RC is very different for those two sides. Because this side is LRS, the other side is HRS. Then this side is going to charge faster. Discharge faster. So then, due to this latch behavior, it will be like 1 and 0 in this way. So the mismatch between the left and the right hand side in terms of the RC delay will determine the data pattern, will restore the data pattern like 1 and 0 due to the resistance difference between those two cells. So you don't need to do anything to write the data back to the SRAM cell. Once you power up the chip, then it automatically flip due to the resistance difference. So this is the principle, and then in this paper, VLSI it implements this design in 180 nanometer CMOS and this carbon oxide RRAM technology, and then it achieves some of the performance like here. The let's say the store time is like 10 nanoseconds. You can write the data into the RRAM, and then you can save the rate of access time. I think this is for the conventional SRAM operation. So the store latency is like 10 nanoseconds. It didn't show the restore latency. It should be in like tens of nanoseconds as well, I think. Here are some data for this design. So in total, the capacity is kind of small, only 16 kilobit for a proof of concept. And then if you look at the store energy versus the store time, if you do the SRAM and flash version, so this is the conventional way. You have your data in the SRAM array, and then you read out the SRAM array row by row and then write into the flash. If you do that, then that is your energy and the latency. But if you do this way, right, so it shows you have reduced the store latency by 10 to the power 6, and then reduce the energy by 10 to the power 5. Right. So because this is very fast, you just need like 10 nanoseconds, then you can store your data. But if you read out SRAM and write to the flash, it takes 10, right? The flash write, like tens of microseconds. So this is like 10 nanoseconds. And this is much faster than the SRAM plus flash solution. So you can also extend this kind of design to latch and the flip-flop, because they are essentially very similar to the SRAM cell, right? The latch and the flip-flop. You know, two latch become one flip-flop.
Is this used by any company? Like this kind of design is used by any company?
No.
This will result in a significant area increase.
No. Looks very interesting, right? So there are practical challenges, I think. This is a chip demonstration from university, and of course they work with industry to demo this chip. But there are some, I think, maybe you can think what are the challenges there. Any idea?
It has to be 3D or?
Not really, because RN cell are integrated in the back end anyway, right?
Logic.
So if you've got a logic chip and now you've got to add the resistive component, now going to start interfering with your metal layouts.
No, because RN technology is CMOS compatible, right? You even doing RN array, your RN is on the metal layer is compatible with the CMOS fabrication.
On the SRAM, we use SRAM much more frequently because it's used for caches. So if we use RRAM, we'll have to write it multiple times, and it's not endurable.
Yeah, this is one reason, but not exact. Okay, so I think there are a few concerns here for practical application. Okay, the first one is you add RRAM to the SRAM. There are some penalty to the SRAM operation speed for the normal SRAM read and write, because you add additional node to that storage node, Q and Q bar. You have additional resistance to that, so the RC delay for the normal SRAM operation will be slower. This is one concern for normal operation. The second concern is what you mentioned, the endurance, but that is not for the normal operation. That is for how often you power down your chip. How often? So you know, RRAM has limited endurance, right? Maybe tens of thousands cycles. That is a limit you can power down your chip, depending on how frequent you do this power gating, right? This also depends on your application. If you power down every microsecond, then after like let's say a few hours, then the chip you cannot use this mode anymore, because RRAM maybe totally break down. So how often you do this? Okay, if you do it every day, maybe okay, right? If you every day you do it once, but if you every day, then it's not that useful, right? So every day you need to even you press the power button and then store to the flash, maybe okay, right? You wait a few seconds and then maybe okay. So this one, if you really you need to make use of this, then you need to make the endurance of the RRAM to be compatible, even when you just switch the app, or not on the scale of maybe, I don't know, milliseconds, or even below that.
Is this for mobile applications specifically, or can this be for a desktop processor? Because very often SRAM is just a cache, so it just stores the most used information that's already in the RAM. So if you only store that small little bit, it may be meaningless if your RAM is lost.
If your RAM is lost, what do you mean if your RAM is lost?
So
this is for this dynamic power gating, right? You want to turn off your power supply and save the energy latency for the standby mode.
But then you would have to use the SRAM for your entire working memory.
Oh, this is just for the this is not to add additional SRAM array. This is on your existing cache. If you each cache, I mean all the cache is equipped with this number 10 memory. Then you just store all the data locally to the RRAM. And I think the second challenge is endurance. The third one is let's say still the variability and the reliability of the RRAM is a concern. So here is unlike the regular RRAM memory array, you have an ECC, error correction. This one, if the RRAM cell fail, then how do you recover this, right? So there are some reliability concerns as well. So, but it's an interesting application if you can realize this with a certain endurance reliability. I think it will help with the battery life for your edge devices.